similar on one.
Let's see how he's doing it. He good. And again, we can see a direct relationship between the schematic diagram and the wiring diagram. And we could clean everything that's in the schematic from the wiring. It would just take an awful lot more tracing of wires to do that. So that schematic is a very simplified explanation of how the circuit is controlled, and this is a real world application of how it's wired out there in the field, or it should be.
Kind of a stick hand version of the picture.
That's right. So, we talked about this already, and again, we've got here nothing more than switches, relays, and lights, and that's pretty much it. And we've got relay coils, and we've got relay contacts, and remember, there is a set of contacts that are true even on some relays, even when the relay coil is not engaged. What type of relay contacts on a relay are true when a relay is not engaged? The normally closed are the true state, and they'll exist that way on a mechanical relay, even when there's nothing hooked. You can hold it in your hand, and literally those normally closed relay contacts are closed. The only way you're going to change the normally closed to an open state and change those normally open contacts to a closed state is what? Energizing what?
The coil.
The coil. Okay. So we seem to have that pretty well down, and hopefully by now we know the difference. What type of contact on the relay are we talking about there? Normally open. If it were normally closed, it would have the slash, and the slash connects both sides, so that's a closed state. So an open state is the two parallel lines without the slash. So that's the way we can remember that. How do I distinguish between what's a normally open switch there and what's a normally closed switch?
The normally open,
It's a open one?
they're not, they're both the one that don't touch the
It's not
contact.
touching, if it's
Right.
touching, it's closed.
So if I have a normally open switch of the type that we see here, what do I have to do to make it close?
Energize,
Push.
switch.
Or as we say in the South, mash it. Mash that button.
Yeehaw.
So how do I change the state of these normally closed switches right here?
Match that too.
Mash that button as well, or push that button. We'll try to use better English.
You're gonna kick it.
But where's that button for PB4 on the,
4, 5, and 6 are down here.
okay.
So, and it's unusual. I won't say. It seems odd to me when I first looked at the simulator, this seemed like one switch, but it's not a toggle switch. It is two independent buttons. So it took me a little while to get past. This wasn't just PB1, you know, with an on-off state. It is two independent switches, just as we see here. Because I'm used to toggle, not the start-stop, and we've got that. And I know you were gone, but I'll bring that up. And you can see, for those of you that hadn't seen this or want to refresh, that the start button here is normally open right here, and we have to press it to close it, and then the light comes on. And then our normally closed is closed until we press it, and then it opens up. So that's exactly what we're seeing here in the picture. All right, let's talk about some other things. After we turn on the lights are on right now. The machine's operating, it vibrates, and we break that wire right there. What are going to be the symptoms of that error? of that fault.
The relay will not engage.
You won't be able to energize the relay.
Turn it off.
It won't turn off.
Turn it off.
Yeah.
You said that wire breaks.
If it breaks,
If it breaks, the coil will not energize and the relay will not engage. The lights won't come on.
well, they were already on, so what
Yeah,
happens as
that's-
soon as that wire breaks?
They go off.
They're gonna go off because the contacts are gonna open.
I'm hearing all kind of answers. And one of them's right, I'm gonna say something hard.
They won't cut off.
I think they'll just go off.
I'm hearing two mainstream things. They won't cut off, or they'll just go off.
Just go off.
It's off.
They'll just go off. So if they just go off, it would be like having to press one of these buttons and interrupting the lines, right?
Yeah.
So if that wire breaks, it's as if we just pressed one of those buttons and interrupted the lines. So yeah, they would immediately go off by that wire breaking, and you couldn't get them back on.
And it would probably blow the fuse also, right?
Well, it depends on whether it shorts or not. And, yeah, and that's a good point. If this is the back of the cabinet and this is the wire, and we have a break like that, then it wouldn't necessarily blow the fuse. But if during that vibration, the hot side touched that cabinet, then boom, we've got, a problem. And that's one of those.
You can also have a broken wire where the insulation isn't broken.
Right, yeah,
The
you
wire
could be,
broke inside the wire.
it could be nicked, but not broken in two. Exactly right. If I break the wire here, what's gonna happen?
PB3 will not be able to engage the coil, but 1 and 2 will.
Exactly right. We'll be able to turn it on using either PB1 or PB2, but not PB3, and that's provided that break. And if I do say if it's short, I'll let you know it's short. Otherwise, I'm talking about a break. It could be a loose terminal, or it could be something that's hanging midair. What if we break right here? What's gonna be the symptoms? And I'm looking for two. Symptoms.
It's already
One
on.
will work, but maybe 2 and 3 will not.
That's one symptom.
Because there is no path going back. There is coming
It's not
Only maybe one.
gonna, it's not gonna stay on.
It's not gonna stay on.
Yeah.
Yeah, we'll be able to press PB1. We'll complete the circuit to the coil. With the coil completed, actually, no,
It will stay on,
it would not come on at all.
Because it's not getting power.
Because there is no
right?
Right.
Not because it's going down to the
Yeah,
bottom.
because we did not engage, we engaged the coil, but the wire feeding pin 8 that's ultimately gonna take us to pin 6 is not gonna come on.
There is no return point.
So here's the symptom. What would we measure relative to ground at pin 2 of the relay? If we press PB1, 115 volt. So our first instinct would be, hey, the relay's getting power, but the lights aren't coming on. We've got a bad what?
Got a bad
We'll have to have 2 bad bulbs.
Well, fat relay.
You'd think bad relay right off the top of the bat, because you're going, hey, we've got power to our relay, it's not cutting our bulbs on. There's mechanical relays, they fail all the time, fixing to run back, get one, be a hero, and dadgummit, that didn't fix it. So then what you're gonna do is what you should have went and done the first time. You're gonna measure whether pin 3 had 115 volts on it when PB1 was pressed, and you're gonna measure whether pin 6 had 115 volts. Because both pin 3 and pin 6 should get 115 volts when the PBs are pressed. So that's good.
So I think every time it says PB,
Peanut butter?
every time.
Oh, okay. Well, it's better than FU. I go over there the other day. I should have put FUS.
A little late now.
We have a blob of metal that falls down across
Enjoy that,
LT1
America.
here.
And everywhere else.
The lights are off right now. But this piece of metal, some shards from the cabinet or something, fall across the terminals of this light right here, LT1. What are our symptoms when we press the on button?
Fuse is gonna pop.
Get blown, confused.
It's short,
It's gonna be-
It will be short, so what's gonna happen?
the light will not go off.
Neither light will come on. What else?
Well, the fuse is blown.
Yep, fuse is gonna blow. And that's pretty much it, it's dead circuit at that point. So, if that's the case, where would we expect to measure 115 volts once that fuse blows?
Only at FU1.
Yeah.
Only from here, I can draw there, from there to there. And as soon as we try to come down to here relative to neutral, we're gonna measure 0 at that point. Okay. Let's come over to our wiring diagrams, maybe be able to read both of these as well. We did this before, but we'll do it again. We break right there. What will we see symptom wise?
Another light bulb will engage.
Okay.
The lights will not come on, yeah, lit.
LT1 will do it.
Another bulb will energize.
Your relay will engage, but neither bulb is gonna work.
Right.
Bingo.
Right, that's going to be neutral.
Yeah, we've got 115 volts on this side,
But it's going to
but
be.
we don't have it here. Well, excuse me, if we reference here, I should say. Let me go back, I kind of missed where I was heading, so I said 115 volts, we're taking neutral. Let's follow our neutral. Remember, we have to have that circuit, so we have to have a path from line to neutral to light a bulb. Well, this is going to the neutral of that one. This is going to the neutral of that one. And the only way we're tying back to the neutral at 115 volts is literally this way. So with that said, we're not providing a neutral to either bulb. So, you're right, neither bulb with light at that point. Now let's talk about where, I'm gonna put a probe on ground. I'm gonna put a meter probe right here on neutral or ground.
No,
Remember, neutral and ground are what?
The same, when you're
The same.
setting voltage.
It doesn't matter if I put my probe on N or on G, both of those are bonded together in a separate cabinet. So the black probe is right there. What am I gonna measure if the red probe is right there?
Nothing.
0. Very good. Because my neutral's open,
Yeah.
so I've got no path back to the neutral line. And that, anyway, that was a, did I put it on the L or N?
You put on the L.
Okay, good, that's where I meant to, I just wanna make sure. All right, what would I measure there?
Same.
Same being what?
Zero.
0, right, again, my neutral is, opened up to my lights, and I would measure 0 volts. Now, looking back at this guy over here, what am I gonna measure on pin 2 of my relay?
115.
But you're still getting power.
Yeah.
with that.
Yeah, we're still engaging the relay coil. Nothing about this neutral opening up has stopped that, right? The relay coil is still engaged at this point. So we're gonna read 115 volts there. Now, fun question. What am I gonna read there?
115.
115 volts, right? Because I'm still taking 115 volts into pin 1. The relay coil is energized, so I'm still carrying that 115 volts out to pin 3. All right? What about right there? Pin 6.
Still get there.
Zero.
In 6, you'd still get there.
115.
Zero.
Zero.
if you're gonna get zero at the screw on LT1, you're gonna get zero on the wire too.
I'm still up here with my flag.
That's the hot ones, you're gonna be wearing a brace.
Okay.
You still have no path back.
I got 115.
Yeah, because you checked on
I
that side of the
think
break.
you're going to six. Not to LT.
Because I'm still applying 115 volts here
To that,
to pin 1, same 115 volts I'm
Basically,
supplying to pin 8.
6.
So,
That's the same
all the way to the side.
I would, that's same, this is really the same as this L, right?
He's right. Shoot.
So, well, yeah, I measure 115.
That's one of my own here.
but I
Lindsay,
thought the LT one wouldn't give you all that.
No, we'd get 115 here, we just wouldn't get across the bulb itself. We'd get it relative to neutral,
Okay,
because the neutral is opened up, so we're measuring, literally, we're measuring that side instead of that side. That's the difference, but we're measuring before the break, not after the break.
No, carry on wood. Trying to curb a person. Be creative somewhere.
Let's see, let's think of something else. All right, this part of that relay goes bad.
Define bad.
No longer, the contacts no longer close when they should.
Oh.
7 and 8.
Lights.
No lights.
All right,
What about when they-
so once we press either PB1, PB2, or PB3, where on this schematic, relative to ground or neutral, would I measure 115 volts? Name some places.
Pin 8.
What?
no,
Is
you
that
wouldn't pin eight, you would
three?
pin one.
R1.
R1,
Eight and 6.
is 8 and 6?
All right, one at a time.
R1 8.
I'll take yours.
Because it won't go to
R1,
six.
pin 1. All right? Anybody else? Raise your hand if you got an answer.
PB3, pin 1.
PB3, pin 1.
R1 8.
R1,
Pin 8.
where is
The
R1?
left side of the bad
Oh,
contact.
yeah, right
Oh,
here,
yeah,
the one I wrote the X over.
Pin 3 on the relay.
Pin 3 on the relay, yep.
PB1 and PB2,
PB1 and PB2, pin 1.
What's that number on the left side of the coil? R1?
2.
2?
Yeah, R1, 2.
R1 2?
R1
Right here.
Yeah.
I got that.
All right, what else?
R1 7.
R1, nope,
No.
Nope.
because that's neutral. If you went neutral to neutral, there's no difference of potential. But I see where you're coming from. But there is a difference potential across the
Really,
coil.
everything between all your green circles.
So you're saying I would measure it here, 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 here.
Don't forget.
Jawohl.
And our fuse, yeah.
Basically, everything with your lighting is part.
Exactly.
Everything before, really.
Yep. Because what's happened is, the only thing that changed that didn't change states is that relay contact it should have. So, when we press PB1, PB2, PB3, and if 1 and 3 closes, then this 115 that's here is at the same potential here. So that puts 115 volts in this entire line. We've already got 115 volts up that entire line. None of the off switches are depressed or pressed. So we've got 115 volts all the way to pin 2. We've just got a relay. So the next time you're checking a relay, if the lights aren't coming on, the first thing you can check is, do I have a potential difference on pin 6? Am I measuring 115 volts? If not, you got a bad relay.
Wouldn't you also be reading voltage at pin 5 on the relay, being that the contacts didn't change?
You would, but that's an unused pin, but yeah, well, not necessarily, because like the one we had down there, Josh, and that's a good point, though. That is a very good point. If it's welded to that pin 5, then yes, you would read, but if it's migrating, but just not pulling all the way over, if it's migrating away from the normally closed, but not hitting the normally open, it can literally be in between. So yes, maybe. But not definitely,
Typical.
not definitely. So that's a good point, that is a very valid point. All right. This part of the, well, let's not use green, that means good. This part of the relay goes bad. First, what are the symptoms?
It'll
The
come on,
coil-
but it won't latch.
The coil will engage but not latch.
Let off of the push button. it's
Does
gonna
that
go
go
off.
to the floor?
That's correct. We could press PB1, the lights would come on until we let go of PB1. We could press PB2, the same thing would happen. We could press PB3. And that's simply because it's the inverse of what we had before. The lights are gonna cut on when the relay coil is gonna engage. What's supposed to happen is both contacts are supposed to change state. This one changing state to provide a path for the lights. This one changing states to provide a latch for PB1, PB2, PB3. But it doesn't. Something happens. It does just like a relay we played with down there in the lab. It moves part of the way off and doesn't ever hit the other contact. So as a result, we're not latching it on, but we do see it come on. So let's play that same game. We've got a meter. Let's do it on the wiring. Let's do it here. We've got our meter here across our neutral or ground. Where, well, we'll do it over here, doesn't matter. Where over here, if we're on neutral, we got our black here. I think that's where we did it a while ago. Our black right there. Where on this circuit, once we let go of the button, are we gonna measure 115 volts?
All the way down the left side of the schematic.
Yep, which is a no-brainer really, because this is connected to line, 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 and that's connected to line. So that doesn't change it any whatsoever. Now, I decided to try a new tactic, and I'm gonna hold a button down while I'm measuring. So I'm pressing either PB1, 2, or 3, keeping it in the normally closed position. So I'm gonna come up here and press this guy, or this guy, it doesn't matter. Where now will I read 115 volts as long as I'm holding that button pressed?
All across.
Everywhere except for 2 and 3.
Right here, right here, right here,
We have a lot of third
The light.
right here, right here, right there, right there. Where else?
Across the button.
All the way across there, right? Where won't I read it? That should be a clue to us.
R13.
Yeah, 30.
Right. I will not have 115 volts here. And that should be a clue because if I've got 115 volts across R1
And
pin
it's not.
8 to pin 6, I should also have it the other way as well.
It's not closed.
That's what I'm saying. As long as,
Wait a minute.
as
You're
long
holding
as,
it
as
down.
long as you're not pressing a
He's holding
PB,
it
right?
down,
If you're holding it
If
down.
you're holding it
you
down,
got
you're
a
gonna
path.
read it.
You still got a path.
Okay.
But you still won't catch the 115.
Oh, yeah, very good.
You
You
will
don't have
have
that.
Still have it there.
You will have
Yeah, you're absolutely right.
But
Yep.
Stay.
Manually.
So see,
As
even
long
we
as
trick
you're not
ourselves, I
pressing.
trick myself into believing that when it's not true. And that's
Good
one of the things you'll
salesman,
get
I
into troubleshooting that you will do. Yeah, you've got a path there.
Yep.
So you would read that voltage there, but it's not the voltage that's coming through on pin 1 that you're reading, it's the voltage that's coming across pin PB1, PB2, and PB3, whichever one you're holding now. So yeah, so,
What if those contacts welded together?
welded which way?
What if they welded together?
Welded which way? Open or closed?
Closed.
Closed, then you wouldn't be able to turn them off.
Right.
Well, you'd be able to turn them off, that's a good one, let's do
You
that.
push the button down.
You
Let's
can
do
give me
that.
an answer now.
No,
I like that,
we just have to change that switch. completely.
I like that, alright. So what has happened is this guy
He was talking about, yeah, on the-
that's normally open, and when we talk about welding together, all that simply means is there's enough energy that comes through there that makes those contacts not release. In other words, there's been some kind of arc gap or spark, and those contacts weld themselves together. So this guy is in a permanently closed state now. We pressed it on, the lights came on, it's in a permanently closed state. Symptoms.
Lights and
Lights
lights
stay
are
on regardless of pressing the PB 6, 5, or 4.
Kind of. We're halfway there.
They'll go off as long as you hold down the, off
Right.
button.
If you,
Yeah.
that's what I was thinking, we hold it down.
If I press PB6 down, they'll go off. As soon as I let go, that path is provided again, and we're gonna go. What is the condition of my relay coil with this guy welded?
It's staying permanently
It's staying
closed and latched, so
latched.
those lights are staying on.
It's going to stay there.
Yep.
It's staying energized.
So our relay would stay energized the entire time until we press PB6, 5, or 4. Then it would release for a moment,
As long as
and
you
then we'll
press
go
it.
right back to do it. Okay. All right, let's take the other guy. This contact welds itself closed. Symptoms.
Can't turn it off.
Lights are on right
Can't
now,
turn it
right?
off.
All right, so what happens, what's the only way I can turn those lights off?
Or one of
Unscrew.
the off buttons.
B,
Any four,
Yeah.
five, six, seven,
As long as I press one of those
Switch
buttons,
to press.
for the instant that that button is pressed until I return it back to its normally closed state, we're gonna see these two lights remain on. So very good way to
Huh?
understand it. Hmm?
Run that by me one more time.
It's the same
No.
as one.
As long-
Yeah, that's
it's
what
the
I'm
same
wondering
thing as
too.
1 and 2 being.
That's right, they're permanently
1
on.
and 3.
They're permanently
And
on,
when
there's
you
nothing
mix
to
it
turn them
down
off.
4, 5, or 6, it's not.
Right,
turned
because
off
the
or
path
something.
this contact is no longer controlled by the relay.
Right.
This contactor is welded shut and it can care less what
Right.
the relay's doing.
You'd have to flip the breaker.
Yeah,
One
that's
button.
what I was thinking, you got a path, no matter what, you got that path.
But you break it on the
R,
first
R1
press it
wouldn't
off.
engage
Not on the
with it.
second.
Right.
Second.
Because your second.
R1 would not
Continuous
That
line,
would stay,
you gotta
would
go
stay
through the
engaged,
stop.
right?
so how can we stop it once again?
You can't.
Or would it?
Have to
Not
come out.
that one, yeah, yeah.
You have to come here.
I'm saying the 1 and 3 contacts,
Even if you press
would those stay
PB 4, 5, and
engaged,
6,
or no, they wouldn't, would they?
do not
Once you
turn
mash
off.
those buttons,
Nothing works.
it's
It just
stays on.
One of those
Ah, yeah,
buttons,
yeah.
Right.
but on the
So we could actually
Even
see
if
the
you break-
lights.
4, 5, 6, right?
So are we correct that we'd actually see the lights stay on, but we'd be able to watch the relay coil change state when we
Yeah.
press the buttons?
That's true.
So how about that? So we just learned a new symptoms. Well, think back to some of these weird things you went through with the simulator and going, how can it be on, not on, and the lights are on? Now you know, at least one thing. There's probably
That
a
was
few,
the time of my life.
few others, but there's one. That's right.
Good.
If it won't stay off, it won't stay on. There's always something.
Somewhere around the relay too. Yep. Exactly right.
Well, not necessarily.
That's what
So PB 1, 2, or 3 welds theirself closed, you're gonna have that symptom also.
Mm-hmm.
Yeah.
Mm-hmm.
So that's welded close up, relay lights can constantly
Either way, it's
stay
got
on.
something to do with
That's
getting
what
power.
you're
So if any connection
Well,
on
it
the
depends.
line side
Like
welds
Josh
itself
was just
shut,
saying,
that,
what if
you're gonna
you
get that
do 1, 2,
symptom.
or
Which
3
helps.
welds in?
As long as you close the circuit,
All right,
you're gonna
so-
have juice.
PB2 suddenly welds across. What's our symptom?
Same thing.
They on, but
Lights are on, right?
they'll momentarily go off
1
when you
and
mash
3
off
engage,
button.
or
Yeah, press the
1 and 3
PB 4, 5, and 6.
close, and
Yeah, by welding that, we're really doing the same thing as that guy, except we're doing it, with the switch instead of the contacts of the relay.
But how would you troubleshoot that to see if it was the?
There wouldn't be a difference in potential
It wouldn't be,
cross.
Right.
Zero.
What-
Exactly right.
There
Black
wouldn't be a
leader here,
There won't be a difference in.
black
potential.
lead there.
With the light stay on the relay. With the weld.
When we measure right here,
The red light, you know, the.
we're gonna measure 115 volts, right?
No matter what you press.
When we measure here, even though we're not pressing a button, what are we gonna measure? 115. We're gonna measure 115 here, here, and here. And if we're not pressing a button and we've got 115 volts across the switches, then it could be this guy is welded shut, but it could also be a shorted switch.
And if you measure,
How
if
do
you
you
took,
tell?
if you took your voltmeter measurements, pin 1, pin 2 on PB2, and there was no change of potential with it open, that means that would tell you it was shorted, right?
Well, you're gonna have a change of potential simply because this guy's supplying it here.
Now, if you measure from pin 1 to pin 2,
Yeah. Because see I've got the 115 that's coming through this welded switch is being provided right here and right here.
okay.
So it's still there. So that's where we have to go from volt mode to on mode.
Okay.
We're gonna shut our power off. We're gonna have to change our meter status to ohms, or we're gonna have to ohm out. That's
I forgot you.
Yep. So that's where it gets a little wonky in our minds sometimes, is just like a while ago when I tried to say that about that thing not having power. Yes, it does. It's provided by something that's in parallel with it. And that's why understanding parallel paths is, and your mind thinks that sometimes it has it perfectly down pat, and by golly, it's gotta be this way, but you have to think.
That is confusing to me, because if it's got, like, see what I'm saying, if it's got 115 on this side, 115 on this side, that's going through, if you measure it right there, you're measuring 115 on both sides, so, did you still get a reading of 115?
Yeah, relative to neutral.
No, I mean like one pin.
Oh, okay, yeah, let's explore it. Well, you would get a zero potential across all of them, because they are at the same potential. So this is, let's call this A and this B. Under normal off conditions, A is not connected to pin B until we press the button, right? But this guy's shorted. So A becomes automatically connected to pin B. So whatever I'm measuring here to here, I'm also measuring here to here, here to
Like,
here.
if they're all supposed to be off and the circuit's de-energized, and you're still reading across, but you still read across the other, so you.
Right, that's
you
where we
couldn't
got to
tell.
break out the old.
I got you, yeah, you couldn't tell it at all.
Very good. All right, a relay is, fill in this blanks, a relay is an electrically controlled what? Switch. A relay is nothing more than a switch. So I'm gonna go back to the schematic.
Kinda depends
I'm
on
gonna
whether
ask
it's working
you to
for you
tell
or
me
against
something.
you.
It's on it.
Oh, look.
Oh, no,
All right. I want you to turn this lamp on. There's one other switch we don't have it on. You're gonna have to add in a normally closed switch. I'll write it on the paper. Normally closed switch. There we go. All right.
Get your little handle.
So I want you to wire that circuit identical to the other circuit, with the only difference being instead of having 3 switches that turn it on and 3 switches that can turn it off, you've got 1 switch that can turn it on. You've got 1 switch that can turn it off.
Wouldn't you need to change the switches to push buttons?
Yeah, we could. We're just gonna use what we got. Yeah, you're right. Technically, he's right, guys. Let's make it right. If we're gonna do it, let's do it right. Okay.
How'd you get that?
You can. How did I do that?
That's not
Figure
good
it out.
to do it.
Go away. There we go.
He already gave it to us before.
All right, so this is a 120 volt AC lamp right here. This coil is 24 volts. I'll write that next to the coil. So we've got to engage the coil using 1 source, switch the power from the 120 volts through the contacts of the coil. And then we've got to be able to break that lamp, shut it off using the other switch. So 1 switch turns it on. I'll tell you what, let's start with, forget about, right now, don't use this guy yet. use just this guy. I want you to turn it on for me. That's all.
If I got out to use, I couldn't see what you
It's
were.
normally closed.
Normally closed.
One normally closed, one normally open. Ha, I drew my normally closed wrong. Should be under here.
There you go again.
I need some blue out.
You got your thing on there.
Or, that burnt.
Monday morning.
Hey, I'll pass this back around. You can see, you can look at this number on top, it says 12 volts DC, that's the coil voltage. And then you'll see on the side what the contacts are capable of handling. So you have to make sure that whatever is turning the coil on and off, engaging the coil, for lack of a better term, is the right voltage to do that. And sometimes there's a range. So even like 12 volts, maybe 9 to 16 or something like that. So it doesn't have to be dead on 12 volts, but somewhere in that range. And we can actually activate that with a 9-volt battery. Plus, you have to be able to make sure that the contacts are capable of handling the voltage. Not only the range, but the type, because there is a difference in the AC and DC contacts on these things. So this one can handle 24 volts AC, what's supposed to engage the coil. The contacts themselves can handle this 120 volts. So we're going to start with the basic of wiring the coil. So what do I need to wire the coil using this toggle switch I've got here? So I've got to apply power to the coil, and I want to be able to apply it when I flip the switch closed, and when I open the switch, it goes away. So how do I do that? What's the first step?
From power to the open switch.
So I gotta connect my switch to the coil, right? So I can go ahead and take one side of my switch to the coil, right? And so I can connect this side here, right? So what do I do now with the other side of the source? Other side of the coil. Other side of the coil. So what literally happens here is when I close that switch, the top part of my source is going to the coil already. The other side of my source is going to the coil via the switch. So that switch now has the ability to open and close the coil, or engage and disengage is actually a better term, that coil. So now that we have control of our coil, we can route something through its contacts. Again, we're electrically operating this switch, oddly enough, with a switch. So now I want to control this light. Now, this is a whole separate circuit. This is really one part of the circuit. This other part is completely isolated from what we're about to do. So I want to turn on that lamp. That lamp's a 120 volt lamp. So what have I got to do? What's step one?
From one
The
side.
source to common
120 to the lamp.
Alright, so we'll take 120 to the common. I heard some of you say to the lamp, it really doesn't matter. So we're taking 120 volts to our common. Now what do we do? Let's follow that path on. Which one do we use? Normally open or normally closed?
Normally open.
Normally open, because we want it to turn on the light when the coil is engaged. So what do we do with that normally open?
Take it to the lamp.
Left-hand side of the lamp.
We could put it to the left, or because it's conveniently located, I'm gonna put it to the right. Really doesn't matter, 120 volt bulb, don't care. Like honey badger. Don't care.
Honey badger.
take it back to your source.
Now I gotta take it back to my source. So, independent circuit, switch operates coil, contacts change, and when the contacts change, the 120 volts that we're applying to this common go through the normally open to one side of our lamp, out of our lamp, back to our source. Electrically controlled switch, completely independent, two different source voltages, got 120 volt source for our lamp, 24 volt AC for here, but this could be a 9 volt DC source that we're switching. Again, they're totally independent of one another. It's just a matter of what we want to use for the control side of the relay, what we want to use for the output, and we've got to spec that relay based on the voltages and types that we're dealing with on either side. All right, so it's just, everybody got that? Okay, Josh is yawning, and that's a sure sign I'm boring him. So, same thing, except now we've done away with our normally, our toggle switch. We've gone to normally open and normally closed switches. So now, same rules apply, except we're going to have to incorporate a latch into this puppy. But remember, they're independent sources, or independent circuits, I should say, not sources. Well, they are independent sources too. Take it step by step. Build the circuit first that controls the relay coil. Build the circuit that turns on the light, and then build the circuit that latches that light on. So you really got three circuits. One that engages the coil, one that turns on the light, one that latches the light. If you'll take it circuit by circuit by circuit, I think you'll get it. So we'll run down the hall just a minute, and I'll be back. Then we'll do it collective. Relay engages. These contacts change state. Our light comes on. These contacts change state, and we're taking 24 volts through our normally open, through this normally closed switch, and we're putting it right here. So if I'm holding that button, that same 24 volts that's right here is going here, but it's also going through my common, out of my normally open into here. But the situation changes when I let go of that button. This coil is still engaged because we're still holding 24 volts here, which is keeping the coil on because it's attached to the coil side. When we interrupt it, poof, out go the lights. That is a latch. And that is the third part of that circuit that tries to throw us when we start talking about latches and latching a circuit. But that's all it is to it. It's a bypass for the switch once the switch is engaged. And that's the beauty. It doesn't become high until the coil is energized. Once the coil is energized, it's high until you press the normally closed switch. Then it opens right up, coil drops, no more voltage. So, kind of a neat circuit, and I think I'm seeing some folks really start to get it now. So I'm going to ask us to take a 20-minute break. We've got an individual with his keys locked in his car next door. I'm going to try to help them. So we'll come back in at 10:05. If you need some more time on this, be right off the bat. And if you're not careful, you'll make some broad assumptions, just like I did a moment ago when we were troubleshooting. So don't just apply the shotgun method of troubleshooting. The shotgun method just basically says, I'm going to change something out until something fixes it. And this is a good way of getting there. This next page is kind of some of the observations you made, what you noted is working, what isn't. And that's a good thing to do straight out of the gate until you kind of get used to it, simply because it's easy to get mixed up. If you've worked on that piece of equipment before, oh yeah, I remember the relay wasn't engaging. Oh, wait a minute, that might have been time before. So noting those observations down, especially until you can get a little more intimate with a piece of equipment, is not a bad idea. So that's the first thing you should have. You've already seen one of these. And that's this guy. And the reason we didn't staple these is pretty simple. They refer to one another, and we didn't want you to have stuff stapled together that you might want to lay out side by side. So we kept those separate from the rest. Does everybody have one of these? This is called a fluid processing control circuit schematic. It'll look like that one you had before, except on steroids.
So you should have 5 sheets full of.
Should have 5 sheets, this should be one of them, 5 independent sheets. That page 2? Okay.
Well,
I'll
it'll tell you
just start
bottom,
with page
bottom
one then.
corner.
Well, this is page 1.
It says 1 of 5 at the bottom.
Yeah, he just noticed that for me. This is page 1. So you're getting into the world of 3-phase. And we're gonna find out we can control 3-phase devices with single-phase relays and such, or contactors. So this is the control, so you should have that. That's page 1. Page 2 is the one I had up there first. Page 3 is,
It's really on steroids.
actually, it's not that bad. It's landscape. There's page 3. Now, page 3 is nothing but a series of terminal blocks, except for these guys here, these contactors and things. The reason we use terminal blocks is it's a whole lot easier troubleshooting a cabinet with a terminal block in there than it is all these wires tied together with wire nuts. So all these little things are junctions. It's where one wire transitions somewhere else from one place to another place. And rather than tying them together and putting wire nuts on, which is really a good thing in a high vibration environment anyway, we use terminal blocks. And that also aids in the troubleshooting process. So that's page 3.
That's exactly.
Page 4, you should recognize a lot of these. What do you see? That's right. It's like the guy from Toy Story. Relays everywhere. Buzz Lightyear.
Nice.
And a terminal block and some other things. And last but not least, page 5.
That's page.
That's the wiring diagram.
That is actually just the control panel box. These are lights and push buttons and relays. No, excuse me, just lights and push buttons. Push buttons and lights.
Same box.
So, what you got here is a wealth of information. The first, let's go back to page 1. Let's start there
On the manual or the schematic?
on the schematic. It calls this one a power circuit schematic. So we're bringing in 3-phase, and we can look what 3 items are being run off of this 3-phase power. And a heater, that's right. So we've got 3 different items that run off of. What do you think PC, MC, Cal, except you, what PC, MC, and
That's not
HC
fair.
stand for?
Control.
Basically, yeah, C, this case is contactor. That's the only difference. And we're gonna learn what a contactor is. I don't expect you to know what a contactor is. A contactor, though, just to give you the short version, is a relay that controls 3-phase power. So, it's still basically a relay. So, yeah. And look what we're doing, we're even taking this 3-phase and we're stepping it down to 120 volts at the bottom. That's because a lot of our control equipment is not gonna be 480 volts. It's gonna be 120 volts. And rather than making the end user have to supply 480 and 120, we're running that through a control transformer. We're converting that 480 so there's only a single power source that has to come from external. And we create that 120 just out of one of the phases there. So it's just a way of saving some time. So that's the first page. So let's go to page 2. We already know what it is, but let's look at it. All right, so we got 120 volts. Where do you think that 120 volts is coming from?
Power source.
That transformer from that power schematic. It even says it up there, in case you missed it, from power schematic.
Okay.
So, we've got all these things that the essence is switches or relay contacts on the left-hand side, or some type of push button, some type of switch, some type of relay contact that's controlling either lights or other relay contacts, right? Just like before. Just a whole lot more of them this time. So we just went from the Christmas tree in our yard to the one that light up there in New York. What we just did.
So
But it's still the same stuff. It's just utilized differently and more interdependent upon certain ones. We're going to get to that. The only difference is you do see with the double circuits, motor contactor, heater contactor, pump contactor down there. So, again, virtually the same stuff. Page, I got 2 page 2, that's right, I already have one. All right, yeah, page 3. And it is called the power panel component. This is the wiring of each of the contactors. That's your pump contactor, motor, heater, and notice.
Overload relays, is that what the bottom is? Is that just overload relays?
Yeah, those are overload relays. The reason we put in an overload relay, and again, you're going to be learning about these one by one. Sometimes motors can be rebuilt and redone. And well, first of all, if a motor goes bad and starts drawing more current, Mark mentioned the other day, even when we're single phase, what can happen to a motor when it's drawing too much current?
It'll burn up.
It'll burn up. Like you said, fire, bad. Because that fire can spread from that motor to other parts of the equipment. So the overload relays simply monitor that motor, and if it starts pulling too much current, they'll shut the motor down, which might mean you can rebuild that motor and fix a problem with it, particularly if it's something that's binding to the piece of equipment before you burn up the motor. Secondly, means you might not burn your facility down, which is another side benefit of it. So that's what overload relays in essence do. And if you look at this contactor, it's got some normally open, normally closed, and normally open contacts there that have a set state when the contactor is engaged or when it isn't engaged. So we can look at a contactor through those outputs and determine is it engaged or is it not engaged. We can control other stuff based on whether the contactor's on or based on whether the contactor's off. For instance, if we had an off light, we'd want to use the set of contacts that are closed when the contactor is off. If we had an on light, we want to use the set of contacts that's on or closed when it's on. So just one example, but far more complex ways. These little things on the side are just some fill-ins of how motors are wired, where they go to and that kind of thing. You'll get to more of that as we go by. Here's some new words. Anybody know what a solenoid is? What is it?
Basically a coil that controls a valve.
Yeah, and it doesn't have to be a valve. There are electrical solenoids, and yeah, it could be a valve, but the principle is the same. Who's got a car with electric locks? You got a solenoid in your car. When you press the button one way, the solenoid fires up. When you press the button the other way, it drops down. Just a solenoid. You got a starter on your car? You got a solenoid. What happens is there's a little sprocket that moves in when you turn the key that connects the starter to the flywheel. That solenoid goes bad, no starting. No gooey. Just sitting there waiting until you replace the starter. So yeah, we got solenoids all over the place, but again, that's the simplistic form of a solenoid. Page 4. Relays. Relays, and just when you think it's safe, more relays. There's 2 relays on here that are special though.
And time release?
Timer
TR1 and TR2.
relays. And again, a timer relay can have, depending on the type of relay, the coil can close and remain closed for a few seconds, then open, or the coil can delay once the timer is activated and not close until a few seconds. And we're going to learn the difference in the timer types. And there's different applications for different ones. Good.
On the time release relays, Lee, is there like a percentage overrun, underrun, like you got a 10-second time release? Are you allowed a variance within 10 seconds?
The mechanical ones are by no means 100% accurate. They're fairly accurate. They're a lot more accurate than you think they would be, within 10% probably. But when you get into PLCs, they're dead on, right on accurate. And it's just a difference in the processes versus a mechanical relay.
Your phone's talking.
Hey, just trying to call somebody. Dr. Pearson Boone, not sure how I did that.
That's how you desk dial, right?
Yeah, I reckon so. So yeah, we're gonna get into those relays and the different way they work. Something you said reminded me of, something else I was wanting to bring up to my phone, started yakking at me. But anyway, yeah, timer relays, different, schematics there, and all. Oh yeah, anybody got an electric heater at home that heats off the coils of the? If you notice, if you've ever measured one of them, or if you ever notice, what happens sometimes when you turn your thermostat to turn your heat off?
It takes a few minutes before it cuts off.
Before what cuts off? The fan. And the reason for that is it's built into it. Those coils, as soon as you unapply power to the coils, they don't go from red hot to cool. They gradually cool off. And that's a timing circuit. So when you cut it off, it goes, there's still heat there, let's not waste it. It'll keep your fan blowing a little longer to take advantage of that heat that would otherwise be trapped. And it probably isn't real healthy for that heat to be trapped in that box either over and over and over again, probably one time, but it would probably begin to degrade things around it if that happens. So keeping that fan blowing 15, 20 seconds, 30 seconds, however long it is a timer relay. And in the heating and air, it's usually called a sequencer, but it's really a time circuit, that's all it is. And last but not least, page 5. These are just lights and push buttons. So we have literally broken this thing down page by page, and I'm going to show you this thing in a minute. But first, I want to get these schematics over here to Mr. Lee, so they can have that same advantage that you guys have. 1, 2. Yep, I think here's one over there.
You need these books
Do you
here?
need a bookstore, Mr.
Yes, there you go. Thank you. To begin looking at the simulator, but we're not going to start the simulator until well within the industrial controls. But the reason I wanted to go ahead and give you these schematics is because a lot of symbology, and I even have went into the industrial controls book, and in some cases substituted some schematics for a piece of equipment they had with this schematic in here and try to reference it, because it's a good translator, it's something we can put our hands on and see versus just a random schematic that they threw in the book. But as we're going through things like contactors and so forth and so on, I think it'll do you good to be able to look at that schematic. And I will say this, symbology is not 100% the same for every piece of equipment. The mechanisms and the components may be, but the symbology is going to vary by manufacturer a lot of times, because there's more, just like the lamp circuit we had a while ago that had the little half sine wave in it. Some lamps are actually loops when you draw them out. So, and on these, it's actually a circle with 4 little lines illustrating a globe. If you go back to one of your schematic pages, I think it's 5 of 5 that had that. You'll see a lamp that has, so, again, the basic idea is the same, it just may be represented a little differently from schematic to equipment. Even sometimes with the same vendor, so because somebody else chose a different symbol than what the other person did. All right, I'm gonna actually go to operate the system, and I'm gonna ask you to, first find my book, top here it is. This thing tells you everything this piece of equipment does, what it should be doing, the levels it should be at. It shows you a cutaway view that lets you see the float switches that's inside. Now you can't, just like in the real world, you're not going to be able to see that beyond what's in the book. But you know there's a switch that floats. If you look bless you. If you look at the pictorial, all that happens is these floats move up. There's contacts on them that close some contacts on there that are actually hardwired to an external source out there. And it's going to go through. I'm going to tell you the basic view of it. I'll let you do all the reading you want to do. And again, we're not going to start this tomorrow. But if you want to go ahead and begin doing it. But basically what happens when we press start is one pump, and we've got a pump up here and a pump up here. One pumps in some amount of fluid, the other one pumps in another amount of fluid. It's supposed to reach around 85%, usually on the sight glass that you see right here, somewhere around that area. Once it reaches that, it begins to mix the fluid after a time, and it mixes it for a certain length of time. It heats it. And the idea is to get to a set temperature, which can be seen on the indicator there. I'm going to zoom in all these. So the process of mixing and then heating it is what blends those two materials. It's just like when we're cooking, we can put two things in a pot and they really won't gel together until we apply heat. The same is true of this process. So it takes a mixing and a heating to get the two right. Once it's done, it's pumped out down to the next station, and we get an indicator of whether the batch passed or failed based on some test. We don't know what it is down the line. We just know that it either passed or failed. Now, just like the other one, I can zoom in on different components. I've got a power switch here. I've got the indicator here. I've got the box here. And I always just take the indicator dial and drop it right on top of itself so I can see a close-up view. And really, that's everything I need to be able to run this process. If you notice, there's a local and remote switch that I can click on, and I can change it to local, which means I can run it from this panel, or I can change it to remote, which means I run it from this panel. So I'm just going to start the process and look at your indicator lights. The first thing you're going to see is intake 1, then intake 2. I think it's heater, then agitator. It may be agitator, then heater. I can't remember. But you'll see these things come on, and then after a time, you'll see it pump out. So right now we're sitting on ready. The power light is lit. If I hit the emergency stop, you can see that. So the lights are lit. Bright yellow means power. Brighter green means none. So I'm in remote, so I'm going to come over here and I'm going to press start. So the cycle light is on, indicating something's happening. The intake 1 light is on, indicating intake 1. Now intake 2. You can see the sight glass is rising to a certain level. We're trying to get to a pre-described 85%. Now we're agitating. There's a motor in there that's blending this stuff. After a few seconds, heater comes on. Once heater is applied, we should see the heater, the temperature rise to the long line that's on the indicator. Once it reaches that temperature, it's going to dwell for a little bit, and then after that time period, we're going to pump out.
It's going what for?
Dwell,
Oh, dwell.
or as I said it the first time, dwell well.
That's what I was wondering.
I made it 2 syllables. All right, so we're on dwell.
Now it's pumping it out.
You can see your sight glass dropping. And we even get a quality indicator on our display here. Does anybody know what that's called in the real world?
I can't see.
HMI? HMI?
What's that stand for?
Human machine interface?
Human
Human,
what?
human machine interface. It's a way for a machine to tell you, what it's doing. That's called HMI. That's one of the acronyms that you can add to your repertoire.
Or FTQ.
This guy right here tells you everything in great vivid detail of that process that we just went through. Now let me show you something that sometimes happens when you're troubleshooting this thing. And again, if I switch this thing to local, I can start it. What can happen is somebody can press the emergency stop. And now we're kind of in limbo, kind of halfway in between. And the only way to troubleshoot this guy at this point is to drain it.
You got to unpress your.
Unpress the emergency stop. Drain it, and then you can begin over. So if you ever come up to the piece of equipment, and notice that drain sounds different than the pumping out. That's simply because we are throwing this away. This gives you no penalty as far as dumping the tank. Now, if you dump the tank 500 times because you're spending that much time troubleshooting it, you're going to get a time penalty, but you're not going to get a wasted product penalty. It will just be based on the time. So I've dumped it 7 or 8 times troubleshooting, maybe more than that, and it's never given me, you wasted a lot of product. And I don't mean your supervisor won't once you get somewhere.
Yeah.
But again, this thing gives you vivid detail of the entire process, what each and every indicator is on it. It tells you step by step, item by item, percentage by percentage, intake, which one starts, which one, tells you how long it should remain on, so forth and so on. So it does a really good job of taking you through. And even to your point, Mr. Tanner talks about on output, which is on page 4, once the liquid reaches 70 degrees centigrade, the liquid must rest for 5 to 10 seconds. So it's kind of liberal in its time frame. So that timer, I'll show you in the cabinet. When you replace the timer, you got to make sure you set it to the right length, or else times won't work as right. So let's just kind of take a minute to explore the system. We're not going to do any troubleshooting today. I wanted to at least see the functionality and different things, and I probably won't cover everything that you can get to simply because it's a very comprehensive little piece of equipment. But let's go over here and open up, and just to go back to that remote versus local. Obviously, this panel would be somewhere nearby the equipment. This one here, this one could be 100 foot downstream at some operators. It shows it all on here for the clarity of working, but obviously a remote switch and a local interface wouldn't literally be side by side in the real world, but we wouldn't be able to illustrate that very good if they really were distance apart like they might be in the real world. So let's click inside of this guy. We'll go over here and apply the key. Arc flash and shock hazard. So better not measure any of this on ohms with power on.
No, because it'll kick you out of it right quick, I promise you.
We'll penalize for just opening it like
No,
that.
no, it
I
won't
done
penalize
done
you
it.
for opening it. It'll penalize you if you put an ohm meter on with power on.
It will definitely tell you to come back later.
So here we got everything from pump contactor, motor contactor, heater contactor. We got our overload relays. We got fuses for each one of those. We got a transformer that sets us down to 120 volts, so forth and so on.
What's the little black dials on the overloads?
Those are actually settings. I don't think you can mess with those on here. It's the time that you can set. Yeah, you can, or you can zoom in. In other words, if it pulls 5 amps for 1 second versus 5 seconds, you know, how quick do you want to trip that overload, basically? So it's a delay. Where if there is a sudden spike, I mean, if you're feeding a saw and it jams for half a second, you don't want to just trip the relay, but if it jams for a second or two, then it might be time to cut it off. So that's our power cabinet, obviously. I love how they squeak. That's really cool. They really do in the real world too. So we come over here, put the key on this one. Then this is alarm, LEDs, reading lamps, heater lamps, cycle lamps, and push buttons. So this is one page of your schematic. If you go to page, five, that left side is the schematic for your page 5 of this guy right here. If you go to page 2, these are the relays that you see on here. And I'm gonna actually operate the process while we've got it. I'll move it at least where we can see a portion of it, if we can see all of it. Watch the relays inside the cabinet.
You're still in local over there.
Oh, I'm a track. All right, here we go. See the relays engaged?
Two of them.
So these will change states as different things happen. So watch the little red lights on the relays. All right, go to the next to last page of your parts list. It should look like this right here. Should have relays on it. Doesn't have a page number, I'll tell you the page number, but it's in your parts list, in the operator's manual. Next to last. Should have 1, 2, should start with overloads and end with timer relays. All right, so look at your relay, which is the next to last component, but really your timer relays are wired the same. They just have a timer mechanism that controls the contact. What is the coil pin numbers of the relays?
2 and 7.
2 and 7, sounds familiar to
Yeah.
all right, what is the common for the left-hand side of that relay? Pin 1. What's the normally closed of the left-hand side?
4,
4. What's the normally open?
3,
All right, what's the common on the right-hand side?
8,
8. What's the normally closed
5,
and normally open?
6.
There you go. Just like before. Exactly like before. And that's pretty much industry standard. That's not to say there are not relays out there that don't follow that, but I'm just saying that is pretty much an industry standard. So, knowing that, how many sets of contacts are we using on R2?
You're only using 5.
What's the question?
There's only 2 sets of contacts, 2 sides of contacts. How many of those 2 are we using on relay 2? 1 or 2? 1 or both or none?
1. Well, yeah, you're using both sides. 3, 4, 1, 2,
What's connected? Okay, we got one pin 1. Okay. Which contact are we not
1.
using?
5,
5,
8,
8.
6,
5, 8, 6.
5, 8,
Now,
Oh, okay, yeah.
me too.
We're not using the right-hand contact set, are we? Because if you look, we're not using 8, which is common. We're not using 5, which is normally
Oh,
closed.
yeah.
And we're not
You're
using
using
So,
7?
using the left
They
side.
use 2 and 7.
the 7's
Yeah, the
coil.
coil.
That's the
Oh,
cool.
okay, I got you.
Remember coil versus contacts. I know some of those don't know.
Page 4.
Which relays are using both sets of contacts? Maybe not all normally open and normally closed. R1 is, right?
Yep.
So 1 close.
R4, R5.
R5. You can go down pin 1 and 8 and basically see which ones we're using. Now, they may not all be using, if they've got something tied to common, then we're using both contacts. We may not be using the normally open and normally closed side of both those contacts. But just a quick way of familiarizing yourself with some of the things that's in there. Oh yeah, I was gonna show you timer relays. Now I can click on these guys all day long, nothing happens.
Which guys?
Regular relay.
Oh, okay.
But if I click and hold on this guy, look at the timer. And what is that approximately set to for those of you that can have it?
It was set for
10
5
seconds.
seconds.
Yeah, it
Was it 10?
10?
It was 5.
Yeah, it was
I
five.
moved it, so I'm gonna move it to 20, and we're gonna watch what happens.
Gonna fail.
Oh, that's that. We have to take the skew out of it now.
Yep. Do it for 20 seconds.
TR1 obviously controls the heater.
That would be fine.
No.
So it's time delay in between agitation and heater that we leak.
And the
Let's see if
second
it's
one
fine.
is how long it takes.
How long the wells?
The heat is until we get to the well, yeah. Second timer is. But wait. Oh, it's
Delayed.
No, it's
Delayed.
failed, okay, sorry. Delayed or whatever. So yeah, we got an error. What's wrong?
It was delayed.
Yeah, timer was wrong, yeah. So I have to go back, and that's why I say if you ever replace one of these timers, they come off the shelf with a preset time. You better make sure they go back to the time prescribed inside of your, manual there, or you're gonna set them out.
First one was closed.
Is there any way to change the level on the tank if we overflow it in the simulator?
No, we'd have to, actually change out the float switches with, and the only thing we got to change it out with is one that's similarly set. So let's look at that. Let's talk about the different things we can do.
Overflowed.
I didn't know we could or couldn't, I was asking.
So here's the thing, I'm gonna lock it out. I'm gonna turn it off first. Either my mouse is jammed or something. There we go. We'll lock it out, I'm gonna verify it's dead. Alright, so we've already got some similarities to our other one, it's just a different type of switch. So I can come inside this guy. If I wanna change one of those, what do I have to use? A wrench. Or if you're from South Georgia, a wrench. And notice we can hover over these things and it'll tell us. Look at the look at the time and the cost, $129.50.
Wow.
Fuses are the same. We could do a screw, what do we have to do if we want to replace a piece of wire? Gotta use a
Screwdriver and then the wrench.
The screwdriver is a wrench, and so very similar to our other one. We go back to our wrench. So,
How much was the time? Time on,
that's transform.
I transform, oh,
Yes.
how much was that?
It's a mere $95.
Just weird.
Go inside this guy, do the same thing. Let's replace a relay. $89.95. Now that was on 5 seconds. If we don't change that time back to 5,
What, 30?
we're gonna cost us a little time there. And we hold it down and adjust. So very similar in that respect. Show you up here, these solenoids, you can click it on the tank, you can replace and measure up here. Measuring the pump, you can do the same thing here, you can actually take the wire nuts off.
Yeah, I was gonna ask you to take the wire.
You're gonna have a screwdriver to take the wire nuts off of.
Oddly enough.
Yeah.
My guess they just didn't wanna incorporate a wide array of
Tools.
now you can, and there have been times that I have, and I'm telling you this only for your own benefit, but just like if I took a wire nut off of this guy and I wanted to do a live measurement, I would make sure it was not touching the back of the cabinet before I applied power. This thing assumes the same thing, so you can't actually make live measurements with wire nuts off. But better make sure your meter's on volts, not on ohms, or it'll give you a little frying sound.
You said you could or could not?
You can,
Okay.
And does it make you turn the power off to take the wire nut off?
yes.
And you have to turn the power off and then turn it back on?
I don't remember doing that inadvertently. I've always cut power off to my knowledge. I may have done that, we'll find out. These are your float switches. Now this is the only wonky thing about the entire thing. These float switches are down inside this pipe. If you want to change a float switch, you have to actually do it here.
Really?
So just be it known. Now some of these, when you go to change it out, let's go to change out a float switch. You can either replace it or inspect it. And you can inspect it and it'll say, this looks good, and you just save yourself the time and the money of replacing it.
Yes.
So anytime you see inspect, I highly encourage you to use the inspect first.
But it takes 40 minutes.
It's still an hour and 15 here, so you just save yourself
What's the $160 for the
the
part?
part. You're definitely gonna get gigged on if it's a good part. So it's all in here. It's just a matter of getting to it. I encourage you to play with it, create the login, try to start understanding what these things are. We're gonna go through them in motor control.
Can you actually change the motor
Yeah,
route?
it's a motor box.
Yes.
No.
You can?
Oh, that little box.
And you can also inspect it.
Okay.
So you-
That's your heater, coils right there, right here. You can actually ohm them out, you can measure voltages there on the contacts, so forth and so on. So that's heater cabinet.
So basically, where you have electricity running, you can change out that part regardless. So the pump, the
That's all
valves,
it's really about, is figuring out which components are working and figuring out what's causing it not to work.
What's that there, yeah?
That's the drain.
That's a drain solenoid.
All that solenoid does is push and opens that valve, and when it's drained, it closes that valve back.
So
And
the other little blue thing
Is
on
the
the
out.
right is the
Pump,
agitator?
that's the pump.
What about the box above that?
You can actually inspect the
Yeah, what
pump
about
too,
the
can't you, as
agitator?
well as the motor?
The agitator,
Agitator motor's on top.
yeah,
Okay.
that's zoom out, get that. We got a wrench. $6.95 and 2 hours.
Oh.
Can you get it inside of that segment?
You can inspect it, so it's the same as kind of getting it.
So they're not individual components, but it's not.
Yeah, you can't
Well,
touch
there
it.
too.
It's inspect or.
You said the electrical side of it.
So, pretty nifty, little thing. Again, we're gonna go through all these components, one by one. You're gonna learn the difference between a timer on relay, a timer off relay, the delay, the whole 9 yards, but I wanted you to be somewhat familiar with this, so you could kind of refer back to it as we're going along. This is only more lengthy than what you did before. It's really not that much more comprehensive, except you have to learn to think in terms of if-then type things. It is more comprehensive, but doesn't require a whole lot more knowledge. It just requires a little more depth, I guess.
It's a little more mental stability.
How do we know when we finish the
It is-
simulation?
I've made all sorts of correlations, but you just got off Bellevue Avenue and got onto I-285 during rush hour.
How will we know when we actually finish the simulation? It's gonna tell us up top in that box?
Yeah.
Okay,
Yeah,
so
we
pass,
troubleshoot.
everything's been passed. So everything you're gonna have to have passed on that box in order
Well,
to proceed.
we'll do the same thing as we did before. We're gonna give you a grade, whatever that grade is.
Now, I'm talking about as far as us progressing to the next one.
Oh, yeah, it'll guide you through.
Okay.
Yeah.
Basically, they're trying to.
Let me ask you this, do we mix any chemicals down there?
Yes.
Sure we do.
Yep, we absolutely do. Using non-organic stuff, organic stuff. So, yeah, certainly. So this will translate well. Question?